Hello and welcome back. In section 3.6 we will look at absolute value inequalities. So the approach that we're going to use is slightly different than the approach that your author uses, but I found through the years it has a much higher success rate than the methods offered in this or really most other textbooks for this section. We'll start with just a simple absolute value of x with an inequality. So we'll say strictly less than 4. So if we're asked to solve this, we'll start with our let line. Let this temporarily be an equation. So we pretend it's an equation. We do what the politicians do. We answer the question we wish they had asked instead of what they actually asked us. So we solve this as if it's an equation for now, and then we work back to what is different about the inequality. So absolute value equation, remember we ask ourselves the typical questions, is the absolute value alone? And this is a yes. So then we go on to how many ways can this happen? Absolute value is a positive. There's 2 possible ways in this case, so we make 2 equations. So either the argument could be worth a -4, you can end up with the possibility that the argument is worth +4. If they had just asked me this much, we just throw these 2 guys into the solution set and be done with it. But remember, we actually had an inequality. So what I'm going to do is I'm going to sketch just a quick rough number line. And we're going to test one number in each of the sections. So notice these 2 points, 2 cuts on the number line give us 3 distinct sections. So we'll try out x is, let's say -5, 0, and 5. Plug them into the original. If they work, we keep it. If they don't work, we don't keep it. Absolute value of -5, possibly less than 4. 5 less than 4 is false. So I don't want anything to do with any of the integers back here. Trying out the 0 though, absolute value of 0, possibly less than 4. 0 less than 4 is true. So I want the -3, the -2, the -1, the 0, the 1, the 2, and the 3. We'll talk endpoints in a moment. Trying out the 5, absolute value of 5, possibly less than 4. 5 is not less than 4, so I can't keep that section. Strict inequality, 4 is not less than itself, so we would not keep the endpoints. So we have -3, -2, -1, 0, 1, 2, and 3. So that's what our graph would look like, and our solution set would be just those integers, -3, -2, -1, 0, 1, 2, and 3. And again, since we're still in chapter 3, we're still looking at integer domain. So next we'll look at what happens if we actually have to do a little bit of work to these. So let's try absolute value of the sum of x and 2 is less than or equal to a +5. Again, we use a let line. We start by pretending we have an equation. This also has the advantage that it gives you a little bit of review time with absolute value equations. That's going to be a topic you'll see on the final. So absolute value is alone, it's equal to a positive, so there's 2 ways this can happen. So we set up our 2 equations. Either the stuff inside could be worth a -5, union that up with this stuff inside possibly being worth 5. And then you're just back to solving linear equations again. So we've done that quite a bit in this course. Break other types of nonlinear problems eventually down into just linear equations. So again, the idea is whatever solutions we come up with, those are the cuts that we're going to make in the real number line. And then we need one sort of test point per section. So maybe a -10, a 0, and 10. So could you have picked -8, +1, and 4? Absolutely, as long as it's 1 in each section. So we tested out always in the original inequality. So absolute value of -10 plus 2, possibly less than or equal to a +5. Absolute value of -8, possibly less than or equal to 5, but 8 is not less than or equal to 5, so I don't want that chunk of the graph. Drawing out the 0, we get a true statement. Two less than or equal to 5 is true, so we want everything in between. So here's our 0, 1, and 2, -1, -2, -3, -4, -5, and -6. Drawing out the 10. Absolute value of 10 plus 2, possibly less than or equal to 5. 12 less than or equal to 5 is false. I don't want that. This time we do get to keep the endpoints, however. We had an or equals to, -7 plus 2 is -5. Absolute value of -5 is 5. 5 is less than or equal to itself, so we would keep the -7. Similar reasoning would lead us to keep the 3. So our solution set -7, -6, -5, -4, and we can use an ellipsis, a comma, and then tell the reader it ends on 3. So next up, we'll look at, what did I pick here? 2 is greater than or equal to the absolute value of the difference of x and 9. So again, we'll just start with our let line. Let 2 equal absolute value of x minus 9. Absolute value is by itself, it's equal to a positive, so we'll set up the two equations. X minus 9 could be a -2, x minus 9 could be a +2, and we just solve that. So x could be a 7. This other one will add 9 to both sides. X could be 11. And since this was an inequality, not an equation, that's why we're moving on and putting our little lines in the sand, the +7 and the +11, and doing some test points. So I'll try out maybe a 0, an 8, and a 12. So I want to know for this one, is 2 greater than or equal to absolute value of 0 minus 9? So 2 greater than or equal to +9 is false. So we don't want that. Trying out the 8. Is 2 greater than or equal to 8 minus 9. 2 greater than or equal to 1 is true. So we want the parts in between. So we have the 8, the 9, and the 10. This one does include endpoints, and then we'll see if we get to keep that 12. So is 2 greater than or equal to absolute of 12 minus 9? 2 greater than or equal to 3 is false. So our number set for this one, we keep 7, 8, 9, 10, and 11. So next up, we'll look at 4 is strictly greater than absolute of the difference of x and 3. Apologies on that one. We're going to do a greater than for this one. Less than 4 is going to be strictly less than the absolute value of the difference of x and 3. Again, we'll start this one the same. We'll use a let line. Let this temporarily be an equation and solve the equation. Absolute values alone, check. 2 ways it can happen. So we set up the 2 possibilities. So notice that the argument is still the x minus 3. I haven't turned this into an x plus 3. The argument looks like whatever it originally looked like. It's this sign on the constant that changes. So the first one, I'll add 3 to both sides. So x is -1. Second one, I'll add 3 to both sides. So x is 7. And again, we go to our friend, the test point. So here's a -1, here's a 7. So we'll try out -2, 0, and 8. So first one I want to know is 4 strictly less than absolute value of -2 minus 3. So 4 is less than 5 is true. So that means I do want the -2, but I also want the -3, the -4, the -5, and forever in this direction. In the middle, I want to know if 4 is possibly strictly less than the absolute of 0 minus 3. So 4 less than 3 is, of course, false, so we don't want the stuff in the middle. And the 8 should then work. 4 less than, possibly less than absolute of 8 minus 3. We again get 4 is less than 5, which is true. So that means we get to keep the 8, but also the 9, the 10, the 11, and so on in this direction. And we'll just put some labels on some of these. So this time we have 2 distinct sections on our graph that we'll keep. We've seen that in the previous section. That's where we'll just use our friend, the union symbol. So first set is coming from the negative infinity direction. We have -5, -4, -3, -2. We don't get to keep the -1 because of the strict inequality. 4 is not less than itself. So we close that one up and then union it with the next one that starts at not 7 but 8. 8, 9, 10, 11, and forever, this time in the positive direction. So 2 possibilities there. Alright, so next up, we'll look at a couple of the special cases. Again, we'll start with our let line. Let the absolute value of 2x minus 5 temporarily equal -5. An alarm bell should be clanging loudly in your head. Absolute value by itself, but it's equal to a negative, so on the how many ways can this happen? This has 0 ways to happen. Absolute value equals a negative. That is false. All that means, though, for me at the moment is that I make no cuts on the real number line. So I can pick any integer that I want. So I'm going to test out x equals 0. You could pick out x equals pi over 4. Someone else might pick out x is negative 92 trillion. Will all either be true or will all be false? Which one is it? Let's find out. Absolute of 2 times 0 minus 5, possibly less than a negative 5. So positive 5 less than negative 5 is false. So that means the whole number system fails. Empty set. But if I had, let's say, absolute of 3x plus 1 is strictly greater than a negative 8. Again, I'll start with my let line, pretend it's an equation. Again, I run into this issue that I have the absolute value alone, but a negative on the other side. That's not possible, so we're in an all or nothing situation again. Either all of the integers are going to work or none of them will work. So I'll just test out. I'll be lazy and pick out a nice pretty 1 this time. So absolute of 3 by 1 plus 1. And I want to know, is that strictly greater than negative 8? So 4 greater than a negative? Sure. So that means we have the entire number line here. So you can't miss. You pick out an integer, so our solution set is I, the set of integers. Pick out an integer, plug it into the original, you get a true statement when you're done. As opposed to this one, pick any integer. You could look for 10,000 years picking out values. You're never going to find one that will work. It's an impossible task. Now, I do want to look at a couple other special cases just involving domain issues. So we'll look at absolute value of the difference of 3x and 2 is at least 10. So again, we'll start with our let line. We pretend it's an equation. So either 3x minus 2 is negative 10, union that up with the possibility that 3x minus 2 is positive 10. Notice the 3x minus 2 is copied exactly as it was. I do not flip that sign in the middle. So linear equations, we know how to solve those. So we're adding 2 to both sides. 3x is worth negative 8. Multiply both sides by 1/3. So x is negative 8/3, which is negative 2 2/3. So obviously we're not going to be able to keep that endpoint even though we had this or equals. This is not in the set of integers. The other one, we'll start by adding 2 to both sides like we did the negative 10 problem. So 3x is 12, multiply both sides by 1/3. And x is a positive 4. So I still have 2 places to cut the number line. However, I'm only going to keep one of the endpoints. So here's my 4. So here's 3, 2, 1, 0, negative 1, negative 2, negative 3. So one cut is precisely at the 4, but one is at negative 2 2/3, so between the negative 3 and the negative 2. So I picked my guinea pigs out, so we'll try out negative 10, 0, and 5. We plug them into the original. If they work, we keep them. If they don't work, we don't keep them. So absolute of 3 by negative 10 minus 2, close it up, possibly at least 10. So 32 greater than or equal to 10 is true. So I'll keep this negative 3, but also the negative 4, the negative 5, the negative 6, the negative 10 that we talked about. Everything over here we'll keep. In the middle, absolute of 3 by 0 minus 2, close it up, possibly greater than or equal to 10. So 2 greater than or equal to 10 is false, so I don't want anything in the middle, which makes me suspect that this is likely to work on the end here. So 3 by 5 minus 2, close it up, possibly greater than or equal to 10. So 13 greater than or equal to 10 is true. So we will keep the 5, the 6, the 7, the 8, and so on this way. So then we'll have a union of 2 sets for our solution. So notice I'm not keeping the negative 2 2/3. That's not in the set of integers. Negative 3 is the last integer that works and is in our boundaries that we came up with. Then we union that up with, I do get to keep this one, the 4. 12 minus 2 is 10. Absolute value of 10 is 10. 10 is greater than or equal to 10. So we keep the 4, the 5, the 6, the 7, and so on forever this way. So I'm going to ask you all to try one out. Let's see. Well, that one's fun. So we'll do 46 is greater than or equal to absolute value of negative 5x plus 6. That's an ugly negative 5. Negative 5x plus 6. Close it up. So go ahead and pause that. See if you can solve that absolute value inequality. Welcome back. So hopefully you started with your let line. Let 46 temporarily equal absolute value of negative 5x plus 6. There's 2 ways for this to happen, so we set up our 2 equations. Negative 46 could be the negative 5x plus 6. Union that up with the possibility that the stuff inside was worth a positive 46. The sign did not flip on this 6 nor on the 5. So we're just solving linear equations again. So negative 46 minus 6 is negative 5x plus 6 minus 6. So we subtracted 6 on both sides. So negative 52 is temporarily equal to negative 5x. Multiply negative 1/5 on both sides. So 52/5 is equal to x. So x is 10 2/5. It's one possibility. Our other one, we're going to again start by subtracting 6 on both sides. So 40 is negative 5x. Multiply both sides by negative 1/5. So x is a negative 8. Here's our negative 8. Here's our 10. Here's our 11. 10 2/5 is between them. So then we're looking at our test points, our little guinea pigs, if you want to think of them that way. Negative 9, maybe a 0, and 11. And we'll see which ones work. Whatever ones work, those are the sections that we'll keep. So 46 is possibly greater than or equal to absolute of negative 5 by negative 9 plus 6. So 46 greater than or equal to absolute of positive 45 plus 6. So 46 greater than or equal to 51, no deal. Then we'll try out the 0. 46 possibly greater than or equal to absolute of negative 5 times 0 plus 6. 46 greater than or equal to 6 is, of course, true. We want to keep the negative 8, but we'll also keep negative 7, negative 6, negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we're expecting this 11 to fail. So 46 possibly greater than or equal to absolute of negative 5 times 11 plus 6. So 46 greater than or equal to absolute of negative 55 plus 6. So 46 greater than or equal to, that would be 49 is false. So we don't want this chunk of the graph. So then our solution set for this, give me, I'm running out of room here a little bit. We'll start at the -8, -7, -6, -5, dot, 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 but we don't continue forever. We continue until we reach the 10. We do not include the positive 10 and 2/5 because that is not in the set of integers. If we expanded to the real number domain, we would get to keep the 10 and 2/5. Integer domain, we do not get to keep that. Okay, so that should give you enough practice from the exercises on section 3.6. So please, please, please reach out with any questions you have, and I will see you next time. Stay safe out there.